Good morning. Thank you for joining me for our talk, eBPF Elves Jumping Through the Windows. And before we get started, I'd just like to thank the Ekoparty organization. This is my first trip to Argentina, and I've been having a wonderful time this week. I gave a training on some fuzzing stuff earlier in the week, and this talk we're going to talk about a new technology in Windows. It's eBPF is coming to the Microsoft Windows operating system. And we're going to talk about how I did a security deep dive on that to understand the architecture and design, and also ended up fuzzing it with different tools, both in the user land and kernel stack. So I am Richard Johnson. I'm a senior principal security researcher at Trellix, and formerly of Oracle, Microsoft, and Cisco Talos. Generally, I spend my time finding bugs and doing fuzzing. And this year I was privileged enough to have a couple of interns with me that I'd just like to credit because they did help out with this work. So Casimir Schultz and Andrea Fioraldi. Andrea is one of the authors of libafl, AFL++, and so on. So we're going to discuss the origins and applications of eBPF, the architecture and design for bringing it to Windows, the attack surface and APIs and interfaces that are available in that system, and generally the methodology for fuzzing large systems that cross both user and kernel boundaries. So before we get started, can anybody give me a raise your hands if you've used eBPF before, if you're familiar with eBPF. Yeah? Okay, so maybe a third of the audience. Now, in the abstract, I actually did advertise that we would do some real-time bug discovery. So before we get the talk really started, let me flip over here and get into my terminal and run a couple of commands. I'm going to run 3 different fuzzing scenarios while I'm talking, and by the time I'm done talking, we'll have some new crashes that we'll be able to analyze. The first one is going to be in the verifier, which I'll explain here in a little bit. But it's basically a static analysis system that is trying to ensure that the eBPF programs that get loaded are secure and not going to break out of the sandbox. And then the VM itself that runs the eBPF programs runs both in a interpreted and JIT mode, so we're going to be fuzzing those all in the background. One more. Okay, back to the slides. So what is eBPF? Well, it's basically a virtual CPU. It's a very simplified RISC-style CPU that incorporates the ability to sandbox code, much like V8 or Lua or something along those lines. It's an extension of the original Berkeley packet filter, which if you use TCP dump and you put in a filter like I want to see only packets going to port 80 on TCP, there's actually a compiler inside there that compiles that down into a bytecode, and that bytecode is actually eBPF instruction set. So it's designed to be a safe system to run code in the kernel that's an alternative to writing custom kernel drivers. It was developed in 1992 as a way to do high-speed packet filtering at the net filter layer. And it was implemented for most Unix-style operating systems, including Solaris and BSD and Linux and so on. And we now call this traditional interface the classic BPF. It was a 32-bit instruction set and was limited to only network filtering. In 2014, Linux kernel 3.18 released with a new system call called the BPF system call, which extended this functionality into a higher-level API that allows you to hook both network interfaces at various layers in the network stack, as well as hook code locations using the uprobe and kprobe infrastructure inside of Linux. And so you can do function hooks and arbitrary code hooks in user land, and you can hook exported symbols in kernel land. It also includes a persistent data store that is accessible from both the Linux and user side through system call. And these are called BPF maps. And so when I say data structures, I mean like arrays or hash tables or things like that. You can use a system call to allocate these in kernel space, and then from your kernel eBPF driver, store data into these maps. And then from user land, you can have a daemon that reads those maps and then responds and does more sophisticated work like maybe access databases or persistent file stores or things like that. In the sandbox, they don't have the ability to access arbitrary memory in kernel land, so this is the interface in which the eBPF program can write outside the bounds of its small little VM area. And so each eBPF program is technically a single function, and you write it in C language, and LLVM compiler has special support for compiling to this bytecode language, and then it can be interpreted in the VM. You're not meant to read the code that's on the screen currently, but it just gives you a sense of the various functionalities that are below the BPF system call. So there's a variety of BPF program types, and depending on the type of program, that will be the hooks that it has available. So again, a kprobe is a type of eBPF program, or an XDP socket layer hook is a low-level network hook. Or you can also hook in, when network sockets bind or various other stateful transitions within a network connection. So the applications of eBPF currently are being widely used in cloud environments and in Kubernetes. A lot of the development is coming out of companies that have major influence into cloud development, such as Cilium and Falco. And basically, there's applications that are written in eBPF to do network monitoring or function hooking for the purpose of telemetry, for EDR, or also for load balancing in a cloud environment to quickly offload packets to another server in a distributed cluster. So those are the products, and then in user space, those products rely upon one of several SDKs, depending on the language that you're writing in. There's support for these APIs in Rust and C++ and C and Python and Go and so on. And ultimately, these programs get compiled and then loaded into the kernel via a verifier and then JIT process that ultimately executes native code based upon this bytecode language. So right now, if you've interacted with any of these products, you have already been using the modern eBPF system. And in fact, systemd these days, if on any standard Linux distribution such as Ubuntu, will have a number of eBPF programs running just as part of the standard functioning of systemd. So eBPF is really becoming integral to the operating system, and it's becoming the preferred platform for performing telemetry and recording information about a system. So all the future EDR and XDR solutions and things like that are kind of moving this direction, and we're already seeing things like VMware's Carbon Black and Red Canary or Microsoft Defender using this infrastructure. So there has been some talks on eBPF in the past, but they've all been on the Linux side. There was some talks at DEF CON, and myself last fall, I gave a talk on using the Linux program hooking interfaces to do some rootkit style things where you could subvert the loading of libc, or you could inject arbitrary ROP payloads, or I have a gadget that will migrate you into systemd so your rootkit is unkillable. But today, we're going to talk about eBPF for Windows, because while I was doing that research, I was looking at related components, such as an open source implementation of BPF. The standard implementation is open source, but it's GPL license, and somebody re-implemented it as a BSD license library. And I had started fuzzing that naturally, that's what I do, and had found bugs. And then I discovered that Microsoft was going to use this library in their stack. So I got very excited and was very curious how they were going to build the system and whether or not my bugs would still be alive on the Windows side. So May of 21, last year, Microsoft announced via some blog posts that they were intending on implementing this system. And this May, or April, well, I guess February, they released their first minimum viable implementation that implements the network side of eBPF. And they did this to implement the Cilium Layer 4 load balancer, which they are using in, well, presumably using in the Azure cloud space. But right now there's Microsoft, Netflix, Google, Facebook, Isovalent, and a handful of others that are creating this foundation for development of eBPF, and this really shows there's some inertia in the software ecosystem behind this technology, and it's going to become more and more used and integrated into the Windows side as well as Linux. So at this point in time, the Windows implementation implements pretty much the entire network portion of eBPF and also BPF map support. It does not have an equivalent to uprobe or kprobe function hooking yet. The architecture is very different from Linux, where Linux, everything is in the kernel and, again, GPL licensed. None of that code could be reused because of the GPL, and this is all net new code that Microsoft had to create from scratch. Now, this diagram might look a little confusing at first. We're going to go through kind of each component there. If you were to look at that kind of like a grid where there's a top left, a top right, and bottom left. Those are the user land components, and then a user mode system service, like a trusted service, a PPL trusted service, that is effectively considered part of the trusted computing base because in that service is the JIT engine. So the code will be verified and then JITted to native code within this service, and then copied over into the kernel side where it can then execute as though it was a driver. And of course, this doesn't require driver signing. So really the interesting thing about this is you don't have to have Microsoft signing your driver code in order to implement network hooks. And hopefully in the future also code hooks. And then also the kernel mode can operate in an interpreter mode, and so there is also the bytecode evaluator or interpreter that also exists in the kernel. So we actually have the same library in both userland and kernel, and depending on if you're operating in JIT or emulated mode or interpreted mode, you activate different attack surface. So currently they're shipping this standalone, and they have no intent to ship it as part of the operating system. And the reason for that they've discussed via blog posts and presentations is that they want a servicing model that is quick turnaround in case there are bugs. So you can imagine if this is part of the core infrastructure of the cloud, they don't want to have to wait until next patch Tuesday to fix the problems in their eBPF layer. It's MIT licensed, and so you can go read the code. It's a substantial amount of code, but it is available to read, which of course makes reverse engineering the design and the security testing a bit easier. If you wanted to create an eBPF program on Windows, well, you just go grab the latest version of LLVM for Windows, and there's a target output architecture called BPF. And so this is what a simple hello world might look like using the BPF print K API. And you'll notice there's a little annotation above the function name here where it says section bind. That's how you define what type of BPF program this is. And the system call will take the ELF file. So these get compiled into ELF objects, and each function gets put into its own section in the ELF. And we can see here that when this object is compiled, the text section is actually empty, and the code is actually located in the bind segment, which is also a text segment according to the ELF, but it's not the traditional standard text segment entry point. And if we were to use LLVM's objdump to dump the assembly for this program, we would see that it's using an interesting assembly language there. We have both the hex and the assembly output. And of course, this is an unusual language for most because it is the BPF virtual CPU. So a more practical program, you don't need to read the lines of code here. This is just to show you a sense of scope. This program has two maps for storing a list of packets that are going to be dropped and the interfaces, the network interfaces that are on the machine. And then you have the top half of a function here for evaluating the TCP packet using a network hook. And it accesses the packet just like you would in C using the standard Linux headers and can rewrite the contents, or it can drop the packet or allow it to go up to the operating system. So these various types, as I mentioned, there's XDP, which is the lowest level on the network, and I have further research on that in upcoming talks, but also there's network attach points that bind, and C group state changes, and SOC operations, and so on. And there's a small API, there's about 100 functions or so in the API that have to do with giving you access to these maps, or allocating ring buffers, or getting the CPU ID, what process, what thread are you in, things that allow you to then dereference like your current task structure, or other Linux exported symbol data structures. And this is just illustrative for what's in there. So the security model for this on Windows is going to be that, again, we can run unsigned code in the kernel without having driver signing in the loop. So we don't send our new driver off to Microsoft to get verified. The verifier itself is a static analysis component built into the system. Now, what this really means, though, is that the current ACLs do require administrative access to load kernel, driver level code. So in effect, if we do find vulnerabilities in the local system of the eBPF infrastructure, then those are administrator to kernel vulnerabilities. So again, this is a driver siding enforcement bypass. It's still a very valid attack surface these days to get persistence on a machine. Oftentimes attackers are loading older drivers to exploit them to bypass driver siding enforcement, and this is built in a way to do that. So yeah, and I mentioned there's JIT mode and interpreted mode. So on Linux, it has its own static verifier. On Windows, there's a new static verifier that goes by the name Prevail. And there was an academic paper on it, and it's quite sophisticated. And what it's supposed to be doing is bounds checking and making sure that you're not dereferencing arbitrary pointers, or that when you call functions, you're checking the return value before dereferencing them, these sorts of things. The original versions of eBPF didn't even allow loops, or the programs are quite constrained. Originally, they could only have 4,000 instructions, but it keeps evolving, and at this point, you can have up to 1 million instructions. The functions can tail call into each other, so now they're becoming more and more sophisticated, more and more capable, and much more like traditional programs, just built for a different architecture. And as this complexity increases, of course, the static verifier has to keep up with these changes and enforce the same policies across a much more complicated type of program than it was originally written for. And on Linux, it is GPL licensed, as I said. On Windows, they're using this third-party library called UBPF from Google's IO Visor project. And it's one of the components I'm currently fuzzing right now while we're talking. And you can use this standalone to verify. It works more like a chained pipeline where you first run a checker on the program, and then you load it into the VM. Whereas on Linux, they aren't really two separate components. It's just all kind of integrated. What's interesting about UBPF as a virtual CPU is it can be used independently of everything I'm talking about here. You can use it as an alternative to a JavaScript engine if you wanted to load C code, blobs of bytecode that were written for this engine instead, or Lua, for example, is probably the closest analog. The performance is at least as good as Lua JIT, so it's definitely a viable alternative, and it does make interacting with native data structures much, much easier than Lua's strange kind of copy serialization across the buffer. So what are the guarantees that Windows is trying to put in place? Well, the programs need to terminate within a reasonable amount of time, because these hooks are kind of where a firewall would be, right? So you want to very quickly be able to process the packets. They will not read memory outside the bounds of the compiled-in pointers, so indirect pointer references are all checked at compile time. Registers are checked for value ranges to make sure you're pointing within the memory map that's specific to this VM. Same with a stack. Arguments are type checked, pointers are checked for null. And there's a new mode that they're working on where this whole system on Windows can run in an HVCI. Well, first they were playing with enclaves, but an isolated virtualized environment doing the verification and the JIT. That version isn't fully baked yet, so I haven't had a chance to really give it a thorough review. So the attack scenarios here are going to be if an administrator loads a BPF program off of GitHub or off of a commercial product, a supply chain style attack, or just happens across my GitHub and during a compile time event, I can modify or patch the ELF file to trigger one of the bugs I'm going to show you. Or there's the trusted service, which exposes an RPC API, and I thought that was going to be where all the juicy target was going to be, but in fact there's really only one API available there. It's just called load and verify ELF program. But what the service actually does is it talks to the kernel driver through ioctls. So of course there is a whole ioctl layer that allows you to interface with the maps as well as load and verify programs and unload programs and do various things like that, pin them to the file system. There's also, of course, the static verifier itself and the VM itself just simply have to be well written so that programs can't bypass the verifier and write out of bounds. And then finally, this infrastructure ultimately is going to tie you to some native APIs that allow you to do the implementations of the network hooks. Or later, if they add in a detour style code hooking infrastructure, then there will be additional attack surface there. So the first area that we're going to look at is the userland components. So there's a DLL, and this would be where the administrator would be loading an object file off the internet or built a project of a eBPF program. And the open source libbpf project is embedded in this eBPF API DLL. And in that is a parser, an ELF loader. It's doing all the work that ultimately is going to call that one RPC interface that says load and verify this blob of this car array of data. So to fuzz that component, because it's a userland component and because it is BSD licensed and cross-platform and builds on Linux, this is my first approach was just to fuzz those libraries independently, see if I could find crashes, and then take the output, which is a bunch of ELF files ultimately that are supposed to contain fuzzed eBPF programs, and then just run them through the Windows system, because fuzzing on Windows is very complicated and much slower. And so that's what I did. And the first vulnerability I found was a heap corruption, where it was in the destructor of this relocation object. So because these are ELF files, they do have all the things that ELFs normally do, which includes the ability to do relocations and have position-independent code. And so almost every ELF parser I've ever looked at has a problem with doing relocations in some form. And sure enough, this is yet another instance where processing the ELF file as it's taking the bytecode out of the ELF section, it performs relocations before passing it to the RPC interface. And there was a code execution bug there. You can see I've placed our hacker-friendly AAAA right at where the dereference is. So we are controlling a pointer passed to free in this case. Call stack looks like this. It just shows that it's flowing through the eBPF object open call through the readelf API and into the destructor for the raw program that it's trying to release after copying the code it's ready to send to the RPC interface. And if you look at, this just shows how the buffer was allocated in the relocation parsing part of the code. So I consider that to be an exploitable, given the efforts, you could take a controlled free pointer and turn that into remote code execution. Also remember that you have the ability to do arbitrary kernel memory allocations because of these map APIs. And this has been discussed in a previous DEF CON talk, so I won't spend too much time on it. But these eBPF maps ultimately give you the ability to control arbitrary amounts of non-paged pool on Windows. And so I'm the first person to look at the Windows side, and really you can allocate as large of and as many of these data structures and fill them with arbitrary content. So you effectively, if nothing else, have a wonderful non-page pool spray capability to assist with exploitation. So that's the user land component. That's the DLL that you would write an application that links to it to load eBPF programs, or you would use the built-in tools, BPF tool, let me skim back real quick. On this here, it also shows there's an eBPF netsh.dll. On Windows, there's a command line tool called netsh, and it lets you interface with WMI and some other parts of the Windows system. And so there's a generic built-in Windows way to interface with these programs as well, or there's the BPF tool, or you can write your own and link to this library. So this attack surface I just described is reachable through that vector. So going back forward to the eBPF service, so this is going to be the system service that exports that RPC API. And as you can see in the diagram, this service again contains both the static verifier and the JIT compiler. Unfortunately, the bug that I found previously is actually in the path to getting to this code, so it's almost not really fuzzable directly until they fix some of the other parsing bugs. There is a flow from the RPC service, though, to the same functions at the end of the day, as well as through the ioctls. So you don't need to go through the RPC service to hit more exploitable attack surface. And I'll revisit the eBPF service. It turns out that fuzzing a PPL trusted service is already a real pain. In the end, we ended up doing snapshot fuzzing anyways, but that was what would be required to really fuzz this portion of the attack surface. So the Prevail static verifier was the next component I looked at because it is exposed in this system. And it comes with a standalone tool that does the verification of your program. And so naturally I harnessed that. And that's one of the targets we're fuzzing in the background. So let me go ahead and, instead of looking at slides, let's look at what kind of results we have here. So we're looking for the check. Yes. So this is the checker. You can see on the top line there, we're running the eBPF check. And in the time I've been talking, we've already discovered 119 brand new crashes. And I will say this version is from May when I originally did this research. Most of these crashes have now been addressed, but I wanted to demonstrate the results of what was happening when I was actually doing the research. And if we want to see if those bugs are any good, we can run a tool that will minimize and evaluate using a bang exploitable type script for GDB. And let's see what kind of results we have. So it's indexing those 119 crashes, it's collecting code coverage, it's minimizing them, and in just a moment it will have a display for us showing us that in the verifiers portion, most of these are looking like aborts or null dereferences, but nevertheless, this is a verifier, so if you can get the verifier to crash, depending on the architecture of the system, it may get through the verifier and then execute the code. So we have some, not the most code execution class bugs, but we do have crashes and things that will cause the verifier to stop functioning, basically. So, so there's bugs in the verifier component, which exists both, again, in the kernel and user mode side of the system. And if you look at some of those bugs, like here, for example, is one of those null dereferences. It's not, or this is actually, sorry, this is a read AV off to kind of a wild portion of memory, but again, it's just shows what we're testing. It's a smoke test for overall system quality, right? So that's the verifier. Then comes the virtual CPU component. And again, this was a user mode library that I was able to compile on Linux, so I did my fuzzing on Linux for this. And much to the same results. And due to time, instead of flipping back and forth, maybe at the end I'll show you the live output, but I've got screenshots here. So this is what it looks like. You do find crashes. You can run it both in interpreted mode and in JIT mode, which is what I'm doing in the background right now. And in this case, there actually are writable destination memory corruption class bugs. And so, yeah, the results of this was one of these bugs is actually the bug that I was able to reproduce on the Windows side. So again, I'm fuzzing the library independently here, but this library is compiled into the DLL and the system service. And so, yeah, one of these many crashes was replicated on the Windows side, even though I originally found the crash on the Linux. It's the same code, just recompiled. And in the JIT mode, you can see that we have stack corruption bugs and quite a severe impact. This is the output of Bang exploitable on all these crashes. So the majority of those are all exploitable. And here's when it's a double free, I believe. Oops, sorry. Yeah, this is a free on a controlled VM pointer. So then, yes, as I mentioned, so we did fuzz the service a little bit with WTF, but as I mentioned, the attack surface was already hitting the other bugs, so it wasn't getting as deep. So we moved on to the kernel layer, and to hit all the attack surface, the RPC interface would expose us to anyways. And as a reminder, you have to be administrator to interface with the ioctls. These are the various ioctl functions that are available. So there's quite a bit of attack surface here. It has to do with, again, creating and deleting maps. And it's the equivalent of the Linux system call and what it can do. And in the bottom right there, you can see load native programs, the load native module. There's even a way to well, technically you can load just traditional x64 code through these interfaces as well, which is not documented. You just have to read it in the code and notice that there's ioctls there that instead of, you bypass the entire BPF loader system and literally can load native code without signing if you look closely. But back to fuzzing. So in order to fuzz the kernel driver, I leveraged a new tool, it's about a year old now, from Axel Souchet, also known as Overclock, called WTF Fuzzer. And this is a snapshot fuzzer where you effectively take a kernel debugger, attach to the operating system, dump all of your virtual memory, the kernel and user space, and then you have a static snapshot on disk that you can use an emulator, which they use Box CPU. The Box emulator, it's kind of like QEMU if you're not familiar. But they use that to replay and restore the snapshot and perform fuzzing. So you take a system snapshot, you set the CPU registers at where your breakpoint was when you took the snapshot, you hook a few functions like swap context and bug check and things along those lines, and you have a callback where you tell it where to begin in the code and when to stop fuzzing and start a new iteration. And so it really is a tool, if you're into fuzzing, if you're trying to find, especially if you're looking for a way to target kernel attack surface, I highly recommend you check this out. It's distributed, multi-core, can speak over TCP sockets, so you can actually have a distributed cluster of fuzzers and so on. And you can expect up to, up to maybe 800 or 1,000 executions a second for shallow attack surface. By the time we got through our fuzzing run, though, we were getting so deep in the code and sending multiple ioctls. So we were doing stateful fuzzing where we were able to use fuzzy ioctl requests, like a series of them. And this is pretty much the most accessible tool out there in order to do that. So going backwards, sorry. So this is kind of what, it can look as simple as this. This is a fuzzer, technically. It's a dummy fuzzer. It's the template for writing a new fuzzer. But with very little work, you can get in there. And there's a free example that shows you how to fuzz like a socket, and we converted that over to ioctl fuzzing. And so we have a JSON request format that contains a series of ioctls. So each of the body labels there is describing an ioctl. So we just captured a live system. We were just sending each individual request manually, capturing that byte array, and encoding it into JSON packets. And then the fuzzer is able to generate arbitrary number of ioctls in sequence and serialize and deserialize this format. And when you run it, it looks something like this, where in the middle of the screen there, you can see the crash counts increasing. So we did find crashes. And this is what the server looks like. Sorry, I'm due to time trying to push through a little quick. But it found crashes. And so let's take a look at a few of them. So there was several read access violations, memory exhaustions, and so on. One of them was in the murmur3 hash. That ultimately it was reading past the end of a buffer. Call stack looks something like this. eBPF destroy. This is actually just a few screenshots ago I showed in userland and GDB where it was the double free. This is also the same bug. Again, I'm showing you that these bugs are accessible both in kernel land as well as in userland, basically all over the architecture of the system. And for your future reference, these call stacks are in here. And yet another crash. This is a null pointer to your reference. Not that exciting, but again, just shows that this new code is, has many bugs really. And so when we're talking about systems like EDR systems and telemetry systems and core network infrastructure systems being built on this type of code, I mean, it's important to assess the quality of the code before you deploy those sorts of things. So that's why these are in here. So as you, and here's an example of a final fuzzed output. So the earlier JSON blob was one that was an initial template, and then after the fuzzer runs for a while, it's generating all these JSON blobs that describe the sequences of ioctls, and this is, not formatted nicely because, it's a fuzzer output. But as you can see, there's a whole bunch of ioctl requests encoded in this packet with, large arrays of data and so on. And then lastly, there's a new fuzzing technology called NIX. It's a hypervisor-based fuzzer. Instead of taking a static snapshot, you actually do it from a live working system. So in the end, we ended up also trying to use NIX to see if we could get any more bugs. I mean, in the end, I think we reported like 6 bugs, 1 RCE or ACE, and the rest were more stability quality bugs. And NIX was capable of finding bugs. You see the familiar AFL interface here, but it's actually using the hypervisor snapshot engine on the back end. And so it was finding bugs. However, it pretty much overlapped with the bugs that we had found previously. So that was a quick drive through the userland DLL, the user system service, and then the kernel driver that implements the API. And then last, there's the kernel extension modules that implement the network hooks themselves. And for that part, I didn't fuzz. I just read the code personally to do a code audit on it. It's a small amount of code, and it's kind of tricky attack surface, so it was just easier to read manually. And I'm happy to say that fortunately there weren't any bugs that I saw that were like going to be triggered via a packet coming off the wire at this point. So at least, the most critical attack surface where they're putting hooks in the network path so far have been resilient to my code review and our fuzzing overall. And as I said, on the Linux side, they offer uprobe and kprobes. On the Windows side, that infrastructure just simply doesn't exist. Microsoft does have a hooking library called Detours, which is basically trampolines for userland. And I'm imagining that if they have the desire to put code hooking infrastructure into their BPF implementation, then it will look something like that, where they'll tie in Detours. But at this point, really, Microsoft has many other hooks into the APIs already via event tracing for Windows and the infinite amount of subsystems in Windows, so I'm not so sure if that is really going to come anytime soon. So overall, what are the thoughts here? Well, number one, if you're not already aware of eBPF making major changes in our network stacks and becoming a pervasive component of our operating system, you should be aware. There's a lot more in there that is interesting, especially from a red teaming perspective. I'll be giving a keynote at HushCon in December where I'm going to be talking about some new stealth network backdoor techniques based upon eBPF, and also because it's a virtual CPU, that same code is cross-platform from Windows to Linux, and there's all kinds of fun and interesting things when you start playing with eBPF. The other thing to take away here is that Microsoft just went out and grabbed these third-party libraries and put them into their trusted computing base without really taking responsibility for doing the security assessments before I did. So they had a whole year before I started looking at it, and they had just screens full of crashes in the JIT and in the VM, and so people, if you adopt third-party code, you really, at this point, fuzzers are available. It's low effort to go out and do at least the bare minimum security testing. I mean, we just saw OpenSSL, new code checked in and wasn't fuzzed. We need to be fuzzing, so please, if you're interested in that, talk to me. I give trainings. And in the end, we did find one, I would call it a high class, not critical, but high, because it's an ACE, it's code execution bug, but it requires some sort of luring or user interaction or something along those lines. Since all this happened, I will say that Microsoft took notice right away when I submitted my talk for Black Hat, and since May they have been doing fuzzing. They've checked in a libfuzzer harness for these tools, and at this point we're kind of the bugs that I'm finding they're finding almost simultaneously, and so it's moving. And finally, from those first screens, there's industry push behind this technology. So again, just be aware eBPF is here to stay, and look for it in various components. And lastly, why am I here even talking about this? Why do I do this research? Well, I work for Trellix. We're an EDR company, and we're just trying to stay ahead of the curve and understand how these things work in the infrastructure and whether or not we'll adopt it in the future. So I've been Rich Johnson. Thanks for your attention, and I hope you have a nice day and the rest of Ekoparty. Thank you. And happy to answer any questions.